Hi everyone, and thanks for joining us today for utilising yield line analysis to identify hidden reserves of strength in reinforced concrete slabs. Today, I'm joined by Matthew Gilbert, who's one of the originators of the DLO analysis method, which is used in the automation of the yield line method and underpins LimitState slab. Matthew is going to be leading you through a short demonstration of the benefits and automation of the yield line analysis before then I jump in and demonstrate how it can be used practically to analyze slabs and determine their true load carrying capacity. The webinar itself is going to last for 20 to 25 minutes, and we'll have some time at the end for questions, which you can type into the Q&A section in your interface. We do try to get round to all the questions if we can, but sometimes that's not always possible in the time available, but we do follow up on any unanswered questions by email in the next few days after the webinar. So without further delay, it's time to get started. So I will pass you over to Matthew.
Thanks very much, Tom, and thanks everyone for joining us for the webinar today. So just fire off with an introduction. What we're going to do, first of all, is just give you a bit of background to why you might want to carry out a yield line analysis, particularly of an existing structure. We'll then zoom in and look at the technology. I'll then hand over to Tom, as he mentioned, to demonstrate the software and also apply it to a case study. And then wrap up with a summary and then a Q&A. So the thing that I think rightly everyone is talking about in the industry at the moment is embodied carbon, and what we have to bear in mind is that a significant part of the whole life carbon of a new building is emitted before the building is even opened. So there's a huge amount of carbon embodied in the steel, concrete, and so forth that's used to form a building. If we refurb and upgrade an existing building, then we can typically get away with of the order of 10 times less embodied carbon than demolishing and rebuilding. However, we need to demonstrate existing stock, and it says bridge stock, but it could be buildings as well. Check that those actually are able to deal with whatever a loading regime that we have planned for it in the reuse case. So climate emergency means business as usual is not really an option anymore. We have to do things differently. Specifically thinking of reinforced concrete structures, clearly depending on when the structure was designed and constructed, we have different design codes that we use at those periods. So CP114, CP110, BS8110 in the UK, but clearly overseas there are many other codes that will have been used. And a key thing is that often these design methods were conservative. So in the old days, instead of using LimitState design principles, we had elastic permissible stress principles often applied. We might assume that a two-way spanning slab was actually spanning one way, so introducing conservatism, or we might use the Hillerberg strip, which is a lower bound limit analysis method for the design of slabs. So lots of reasons why we might have quite a lot of conservatism in our existing structure and the design of the existing structure. Elastic finite element analysis methods are often applied to slabs, and these are also prone to provide over conservative predictions of strength. So that implies that there's hidden reserves of strength, and if we can identify those, we can maximize the adaptability of an existing RC structure and also reduce the cost of any strengthening that might be required. So technology, we're using yield line analysis method. It has its origins in the 1920s, and then it was developed significantly by Johansson in the 1940s and beyond. Key thing is it's an upper bound plastic analysis method, directly home in on the collapse load, and get generally a realistic assessment of the slab capacity, considering flexural failure. The downside of it is if we apply it by hand and we choose the wrong mechanism, then we're going to end up with non-conservatism. So on the right-hand side, we've got various different possible mechanisms. Unfortunately, if there's another mechanism that we didn't look at in our analysis that's more critical, then we're going to overestimate the true capacity. So what we've done actually at the University of Sheffield, almost about 10 years ago, first paper published 2014 according to this slide, was to develop something called the Discontinuity Layout Optimization method for slabs. And this is really a systematic means of identifying the critical yield line pattern. And what we are able to do with that method is pose the problem as a large scale but simple to solve linear optimization problem. And so thinking about a simple square slab with fixed supports, first thing we do with DLO is populate the domain or the slab with nodes. We connect those nodes with potential discontinuities, or in this case yield lines, and then we use optimization to find the critical minimum energy solution which corresponds to the yield line pattern of the sort you can see on screen there. Just go back to this slide before I hand over to Tom. Here we've only got a few nodes in the problem. If we put in more nodes, then we end up with very, very close estimates of the true yield line solution for the problem. And if you're interested, there are a number of papers there which talk you through how the method works and also how accurate the solutions are. So effectively with this method, the DLO method, we can get, to all intensive purposes, exact solutions for any geometry that we care to mention. So I'm just going to hand you over now, I think, to Tom, who's going to talk you through a case study and I think also a demonstration as well.
Yes, thanks, Matthew. I'm going to actually take you through two case studies, one using adaptive reuse in a building, as we can see here, and then a second one that's looking at repurposing part of a highway. So for this first case study, we're actually looking at an existing office building being repurposed as an apart hotel complex. It's actually taken directly from a client's case study, but the details have been anonymized suitably. So the two questions that the client was wanting to ask here are, firstly, is the slab strong enough to carry construction loads? And secondly, what loading can the slabs take post-renovation? And works are going to add additional loads from scaffolding and the like, and in terms of site investigation to determine the reinforcement, it was found that the slabs were isotropic with 145 kilonewton meters per meter. Moment resistance, slab portions and beam portions made out of the same grade of concrete, but the slab's 225 millimeters thick, whereas the beam was 600. So here's just an image of the inside of the building with the area that they're considering. And we can see here, this blue portion that goes between the two columns and over the slab is the area that they're looking at to assess in this particular case. Some drawings here. On the left-hand side, we have the area of interest. We can see actually through the middle of it, not seen on the previous image, we have a beam in yellow and a column. And this light blue area is the area that wants to be assessed. In the top right, we can see the different types of construction loading. So we have line loads for the supports of the RMD adjustable props, also point loads that are applied from the reactions of those props on different floors. And similarly, we have point loads for column reactions and pressure loads from the services and the construction activities. And then in the bottom right, just some SI data for the slab. So if we jump into the slab analysis, we can see here, we have the model of the slab itself, and I can select the different areas of it. So here we have the slab, and in the property editor on the right-hand side of the software, we can see that we have a structural definition where we have isotropic reinforcement with MP values for both hogging and sagging of 145 kilonewton meters per meter, and obviously the unit weight of the concrete being 24. We can also look at the beam, and we can see here that actually in the primary direction, the beam is a lot stronger than in the secondary. But perhaps the most interesting part of this model is to look at the load cases. So if you remember, we're asking ourselves two questions. Firstly, can the construction loading be carried? And secondly, what is the maximum capacity of that part of the slab post-construction and in service? So for the first load case, we can see here, we've applied services and construction as pressure loads. We have defined a number of line loads for the RMD supports in different locations. And we also have point loads that correspond to both the reaction forces from the RMDs and also column dead and live loading. And that's for our first load case. For the second load case, we can see that instead of all of that, we now have our self-weight loading, pressure loading from finishes, services, and the apart hotel itself, and finally just the column live and dead loading. At the top of this dialog here, we also have partial safety factors that we can apply to those loads and the actions themselves. And in this case, we're using Eurocode partial safety factors, but equally you could apply whichever ones you felt appropriate. So we have our model, we have our materials, we have our loading. So everything is set up now for us to be able to solve the problem. So if I click solve here, what you'll see is essentially a quick version of what Matthew has just explained about. So the nodes being added into the problem, the solver is looking through the different collapse mechanisms and identifying the ones for each of the load cases that corresponds to the critical collapse load. In the output, if I just look at that, we can see here for load case 1, we have what we call an adequacy factor of 1.45, and for load case 2, we have an adequacy factor of 1.6. We also have this failure mechanism, which is the cantilevering of that bottom left-hand corner of the slab. If I switch to load case 2, you can actually see in both load cases, that's roughly the same critical failure mechanism, but we can animate that as well. So if I click this button here, we can see visually on screen how the slab is failing. So if I just jump back to the presentation, what's that all mean for us? So firstly, question 1, is the slab strong enough to carry these construction loads? So for load case 1, we saw that we had an adequacy factor of 1.45, and that means that the loading needs to be about 45% higher to cause collapse under those construction loads. So the answer to that is yes, we can carry those construction loads. Secondly, what loading can the slabs take post-renovation? And the adequacy factor there of 1.6 means that the loading under those circumstances needs to be about 60% higher to cause collapse under those post-renovation in-service loading. So The features that we've used of the software in this example are we're using these multiple loading scenarios in the same file to analyze both the construction and post-renovation states. We have a set of user-defined partial safety factors, and we've applied different types of loading, so pressure, line, and point loading. And now take you on to the second of the case studies, and we're going to be looking at an irregular bridge slab. So here we can see on the left-hand side, it's again taken from a real-life case study where a client was wishing to repurpose what was a verge on a bridge deck as part of the highway once that had been expanded out to the side. So they needed to know whether or not this section of slab would be able to actually take highway loading rather than reduced loading that you would expect with the verge. We have this trapezoidal shape. We have the loading conditions around it. We can see it's about 4.5 by 7 meters. And on the right-hand side here, we can see that we have our loading, which is in the form of 4 point loads of 82 kilonewtons, which correspond to the wheel loading from our vehicle. We also have an additional pressure load that we want to apply to the slab, which comes from the additional surfacing that is to put on top of that slab. So if we jump back into the software, we can see here we have our LimitState slab representation of that part. If I click on structural definition for the slab on the left-hand side here, we can see that we have our values for that. But again, the interesting thing here is going to be the loading. If I click this button here, we can see already I have 4 point loads set up as our load vehicle. And what we want to do is actually traverse those across the slab. So if I go into the load case manager dialog, we can see here, if I expand the dialog a little, we have our 4 point loads for our wheels. We have the positioning of them. We also have our superimposed load from the additional surfacing. And what I want to do is take those 4 point loads from the left-hand side of the structure over to the right. And it's very easy to do that within the software. I just select which of those loads I want to copy. And then in this dialog here, I can say, actually, I want to move it in the X direction, and I would like 6 copies at 1 meter spacings. If I click OK, I'll get a warning that self-weight and pressure loads don't offset, because obviously you want them to stay corresponding with the slab itself and not moving across. So that's fine. If I OK that, we now have 7 load cases where we can see the positions are moving across. And if I OK that, it's probably even easier to see that using this scroller here. So we have 7 load cases with our vehicle at different positions. For the sake of efficiency in this demonstration, I'm just going to keep the nodal density as quite low. And again, we also have quite a low number of load cases. If we're doing sort of a full analysis, we may want to add more load cases and have a slightly higher nodal density in order to capture the critical failure mechanism. If I come to solve, we can see here what's happening is that the software is stepping through each of the different load cases in turn and identifying the critical collapse mechanism and the associated adequacy factor or factor on that live loading that's required to cause collapse in each case. So again, if I turn on, now it's solved, if I turn on the display of the loads and run back to the beginning, we can see actually as the vehicle moves across, we have a number of different failure patterns, yield line patterns that are associated with the collapse of the slab. And the critical one of those is load case 6. It's identified by this asterisk, and we can see here actually it's folding at that right hand side of the slab where there's no edge fixity. And again, we can animate that and rotate the view to be able to see more clearly how this particular problem is failing in real life. And we can also, if we wish, make a report with a number of different sections in it to tell us how that has failed. So that's just a very quick introduction to two ways in which we can look at assessing the untapped capacity within our slabs. Well, actually, I should mention, actually, this low case 6 had an adequacy factor of 1.39. So we're saying, actually, we can carry those vehicle loads quite easily without any worry about that. But yeah, so we had a look at two different ways in which we can assess the untapped capacity of our reinforced concrete slabs. So if I jump back to the presentation. Sorry, I'm going the wrong way. The question was here, can the slab withstand the additional loading without further intervention? And yes, the adequacy factor of 1.36, that means that wheel loads of up to about 114 kilonewtons for our vehicle can be resisted. And in this particular problem, we used multiple load positions via copying and also application of pressure and point loading within the problem. So that brings us on to the summary. And LimitState slab for adaptive reuse. You can quickly demonstrate the real flexural capacity of reinforced concrete slabs in existing structures and establish the real capacity likely to reduce the amount of establishing the real capacity is likely to reduce the amount of intervention required. We've also shown that the underlying automated yield line technology is both proven and robust, and hopefully this little flavor has shown that the software is also easy to use. You can pick it up and use it straight away. And if you wanted to find out more information about the software itself, you can find that at limitState.com/slab. So we've got a few minutes now that we can have Q&A. So I'll bring this up and see if anybody wants to put any questions into the question box, then please feel free to do so. Also turn on my camera so people can see me. So we've had one question, which is, can you model other edge conditions other than fixed, free or simple that we've seen in the examples? The answer to that is yes. So if I bring up the software. Ooh. Probably the easiest thing to do is just to define a rectangular slab. We can see at the moment this has fixed edges around it, but what I can do is firstly I'll draw a boundary along the inside, and if I select that, we can see that we can actually support internally to the slab with a knife edge support as well as the external ones. And if I change these fixed to simple, we can see we can also have support lift off. And lastly, we can also, if I select this one, you can have partial fixity, where the resistance at the edge of the slab is a factor from the strength of the slab itself. So we've got a number of different types of edge fixity and also internal boundary fixity that we can apply to the software.
I can see there's a couple of questions, Tom, on serviceability limit state. So just to be clear, this software is for ultimate limit state. For serviceability limit state, if you are thinking of an existing building, then if you can, my recommendation would be that you actually perform some in situ serviceability limit state. tests. So in other words, you put in some water tanks, you fill them up, and you have deflection gauges. And the reason I say that is because calculations for serviceability are notoriously inaccurate, and that's for a new construction where you know everything. And it's going to be even more inaccurate when you are coming to a construction that might be 30, 50 or more years ago. So yeah, it doesn't deal with serviceability limit state checks. I think there's actually three of you have mentioned that in the Q&A. If you've got any follow-up comments on that, by all means add them to the Q&A.
Thanks, Matthew. There's another question about ribbed or waffle slabs. Is it possible to model those? Actually, I think there's one of our other webinars has an example of a bridge with ribs on it that I'll link to in the description when this gets posted up to YouTube. But the answer to that is yes. If I bring up the software again, essentially, as we saw, oh, not that one, the other one. In this particular example, all you need to do is separate out the different zones and apply a different structural definition to each of them. So you can quite easily come in and sort of draw in your own sections of slab. And then if I wanted to make that into the rib there, I have no idea what it's going to do to the solution, but we can have a look. But you can imagine that's just going to fail in the same way by the looks of it. But essentially, yeah, you can build up your own model either by importing from DXF or by drawing on screen, as we've just seen, and adding in different zones with different structural definitions in order to make up whatever type of slab you wish. Just having another look. Well, there's a question, what if the rebar patterns aren't uniform? How would you model that? So I guess what I'll do, if I look at the slab here, we can see actually we have the ability to change the direction around which MP is acting. So at the moment, it's just Cartesian, but you could imagine you can put in any value of orientation there, and actually that changes the direction in which MP is acting according to what the direction which your rebar is working in. So that's that. Let's see if there's any more questions. Can't see any, and we're almost at time now anyway, so I think probably the thing to do is to wrap up there. So I'd just like to thank Matthew for his insights, and also to everybody for attending. As I mentioned at the beginning, we'll be making a recording of the webinar available on YouTube in the next few days, and we will let you know when that's available. If the webinar has brought up any further questions after the finish of it, then please do let us know on info@LimitState.com, and we'll get back to you as soon as we can. You can download the software from LimitState.com/slab, and that will have a trial license with it that allows you to use it in license mode for about 14 days. And then finally, please do look out for notifications that we put out mainly via LinkedIn and Twitter to let you know about other webinars that will be happening. So yeah, keep an eye on there, subscribe to us, and you'll be able to be the first to know about any future webinars. So again, thanks to everybody for joining us, and we do hope to see you again for one of those future sessions. Goodbye.